Hello friends, today we are going to discuss about a array. So before going to the array multiplier, let us discuss about what is a multiplier. So a study of computer architectural process, a study of computer arithmetic process will reveal that the most common requirements are for addition and subtraction, but that there is also a significant need for a multiplication capability. So in going to the previous session of videos, we have discussed about arithmetic logic unit design. Under that arithmetic logic unit design, we studied about the adders as well as subtractors parts in it, but we didn't studied about a multiplier in that video. So in most of the computer arithmetic process will reveal about only the addition as well as subtraction part. They are not going to study about a multiplication over there. So a multiplication is a separate one. So here in this video I am going to explain how the multiplier is going to work. So that multiplier is considered as a array multiplier. So see here, this is a basic block of an array multiplier which has a full adder as well as AND gate. Full adder is there as well as AND gate with 4 inputs: multiplier, multiplicand, carry, previous, sum from our previous levels. And also it has four outputs: two from the full adder, one is sum and carry out, and another two are multiplier as well as multiplicand. See here, this multiplier input is here, this multiplier input is for the single block of array multiplier, and this multiplier input is acting as input for the next state also. So that's why this multiplier is an in-out signal. Similarly here, this multiplier is acting as input to this single block of array, and this this multiplicand is acting as input to this single block of array multiplier, and this multiplicand is moving towards the next state. So that's why this multiplicand is also considered as in-out signal. So for example, I am going to uh, take a two numbers 14 and 10, where I am going to product this and how the operation is going to be done in it. So let us discuss about that one. So I am going to multiply the two numbers 14 and 10, where 14 is the multiplicand which are stored in A register with the bits A3, A2, A1 and A0, and next is 10. 10 is a multiplier. The values are stored in B registers with the inputs B3, B2, B1 as well as B0. So see here carefully, I am representing this 14 with a binary representation, that is equal to 1110 and next 10 with 1010. If I product these two terms, if I product these two terms 14 into 10, I have to get the resultant as 140 here. So when I am multiplying the with the least significant bit of multiplier, 0 into 0 all becomes 0. So that's why 0 0 0 0 here. So we have to shift the data towards left side. So that's the reason a empty space is considered here, and that is represented with x. So I am going to shift the data when the bit is multiplying with least significant bit plus 1. So this is our least significant bit of multiplier plus 1, means this bit. So 1 is multiplied with 1110, the resultant will be 1110. So that's the reason 1110. So next shifting, two shifts have to be done here. So two shifts is represented with x, and 0 is multiplied with the 1110 or 1110. So the resultant will be 0000. So in case of multiplying with 1, I am going to get 1110. So now I am adding all these partial products. So each individual product is acting as a partial products. Now I am adding these partial products. Then the resultant is 1 0 0 0 1 1 0 0. So this is my resultant of a multiplicand 14 in product with multiplier 10, right? See here, I've written two statements here. The array multiplier for a 2 4-bit multiplier which is stored in register B and multiplicand register A requires 16 number of AND gates and 12 number of full adder circuits to design. So it requires 16 AND gates as well as 12 full adders. So for n-bit multiplier, the required number of AND gates are n into n, which is equal to n square. So 4-bit means 4 into 4 means 16. So 16 AND gates are required to design this array multiplier of 4-bit wide. So this is our resultant 4-bit array multiplier, and this is also called as the Brown array multiplier. This this schematic schematic circuit is considered as a Brown array multiplier. This is also called as Brown array multiplier circuit. See carefully here. So as I said here, it requires 16 number of AND gates and 12 full adder circuits to design. So that's the reason I taken 16 AND gates here. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So 16 AND gates are used here with 12 full adders. 1 2 3 4 5 6 7 8 9 10 11 12. 12 full adders are used here. So see carefully here. Now I am going to multiply a 14 into 10 here. So multiplicand means a register bit. So the multiplicand should be given here with the inputs A3, A2, A1, A0. So with A3, A2, A1, A0, I am substituting 1110. So 1, 1, 1, 0. I am representing this multiplicand value in A register, where this is our A register values, A3, A2, A1 as well as A0. I am going to place the load, or I am going to load the values here. So the values are 1, 1, 1, 0. So I am going to load the values A3 with 1, A2 with 1, A1 with 1 and A0 with 0. So 14 is represented here, and that value is a multiplicand value. And in the B register I have to load the multiplication. So I have to load the multiplier factor. So the multiplier factor is 10 1 0 1 0. So B3 should be 1, B3 should be 1, B2 should be 0, and B1 should be 1, and B0 is also 0. So when I am loading all these values, so as I had explained here, that a single block of array multiplication means we know that if I want to multiply value 5 into 2, if I want to multiply multiply the numbers 5 and 2, so 5 into 2 is equal to 10. So 5 into 2, so we need to add the 5 two times. Is it clear to you? So where 5 is the multiplicand and 2 is a multiplier. I repeat, when I am going to multiply the two numbers 5 and 2 here, where 5 implies the multiplicand and 2 implies a multiplier. Now I am producting the two terms of 5 into 2. I have to get the resultant as 10, where 5 into 2 is nothing but 5 should be added 2 times in it. 5 should be added 2 times in it. So the same theory is going to be happened here. So here also I am going to multiply 14 into 10. So where 14 implies the multiplicand and 10 implies the multiplier. So the value of 14 should be added 10 times. So when 14 added 10 times, I will get the resultant of 140. So this is the theory behind this Brown array multiplier circuit. So when I am loading the values A3, A2, A1 and A0 with 1 1 1 0 and B3, B2, B0 with 1 0 1 0, I will get the resultant as 1 0 0 0 1 1 0 0. So I will get this value. So see here, the resultant is having how many bits? So bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. So 7 bits is existed here, but inputs are 4 bits here. This is a 4-bit one and this is 4-bit one, but the resultant output got 7 bits, and that 7 bits is represented with P6, P5, P4, P3, P2, P1, P0, and these are the outputs. These are the outputs: P0, P1, P2, P3, P4, P5, P6, and P6. All these 6, 0 to 6 are 7-bit output, where we are getting the resultant as 7-bit, but the input, see here, the input is 4-bit wide, triple 10, triple 10, 1110, 4-bit wide. Here another multiplier is also 4-bit, 1010. So both are 4-bit wide, but the output is a 7-bit wide. So therefore I need a 7 outputs here, and that 7 outputs are represented with these values, with P. That 7 outputs are represented with P here: P7, P6, P5, P4, P3, P2, P1, as well as P0. All those shows the outputs. All those shows the outputs. P7 to P0. All will shows these outputs. So the resultant value which is there here is going to be dropped across these signals: P0, P1, P2, P3, P4, P5, P6, as well as if there is an extra number and it is represented in P7. Next, in going to the operation here, each products can be generated in parallel with AND gates. So see here, I am going to give A naught here, A naught to all the AND gates here parallelly. So each product can be generated in parallel with the AND gates. So each product can be generated in parallel with the AND gates. Here that A naught is giving parallelly to all the gates here, all the AND gates. A1 similarly for this, A2 similarly, A3 is also like this here. And see here, this similarly B naught in horizontal form, B naught, B1 is given to all the AND gates, B2 is given to all the AND gates, B3 is given to all the AND gates. So here the product is the term product, individual term product is working with the help of AND gates. So see here, no need to worry. If 0 into 0 means 0, 0 into 1 means 0, 0 into 1 means 0, 0 into 1 means 0. So the product is existing with the help of these AND gates. Whatever the 16 AND gates are there, that 16 AND gates is providing this individual product: 0 into 0, 0, 0 into 1, 0, 0 into 1, 0, 0 into 1, 0. So 4 products completed here. Next 4 products, so total 8 products completed. So here next 4 products completed, 12 products completed. Next 4 products, nothing but 16 products completed, and these 16 product terms are represented with the help of these 16 AND gates. Here A naught B naught is going to be happen here, A1 B naught is happening here, A2 B naught is happening here, A3 B naught is happening here. Similarly see here, B1 A naught, next here B1 A1, next here B1 A2, next here B1 A3 for this AND gate. Next same, similarly here B2 A naught, B2 A1, B2 A2, B2 A3. Similarly here B3 A naught, B3 A1, B3 A2, B3 A3. So for individual, for every stages, so it is having 4 stages of AND gate array. So for every AND gate stage, so there is an intermediate full adder circuit. There is an intermediate full adder circuits. So that full adder circuits are represented with FA here. So is it clear to you? What I am going to say here is, if 0 is the B naught bit, so this B naught bit is multiplying with A naught here, B naught with A1 here, B naught with A2 here, B naught with A3 here. So the same thing I am showing here. See this B naught with A naught here, B naught with A1 here, B naught with A2 here, B naught with A3. So whatever I explained here, B naught with A naught, B naught with A1, B naught with A2, B naught with A3. So the same thing shown here. B naught with A naught, B naught with A1, B naught with A2, B naught with A3. The next level. Next, this is B1. B1 is this one. So B1 A naught, B1 A1, B1 A2, B1 A3. So same thing here. So B1 A naught, B1 A1, B1 A2, B1 A3. So in this way the product is going to be happen, and all the products are summated here. See carefully, all the partial products. So each individual and array, this is one 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 and array. So total 4 AND arrays, and each AND array consists of 4 AND gates. So total 16 AND gates are going to exist here. So each AND array is providing a partial product here. So total 4 AND gate arrays. So that 4 AND gate arrays here. Total 4 partial products are there. So 1, 2, 3, 4 partial products, and those partial products are represented with these 4 AND arrays. These 4 AND arrays are these 4 AND arrays. First, second, and third, and fourth. These 4 AND arrays, and each AND array is having 4 AND gates. Total 16 AND gates. So array 1, array 2, array 3, array 4. 4 AND arrays, and though each AND array is providing individual partial products. So for let us take example. This AND array is providing a partial product of this one, showing with red color, and this array is providing the partial product of this one, and this array is providing this partial product, and this array is providing this partial product. So all are adding here. So summation is there, and that summation is done with the help of full adders, and the summation is made with the help of full adders. But initially there is no carry. Here see carefully, the full adder will have 3 inputs and 2 outputs over there. So just for example, I am going to explain this part here. I am going to explain this part here. See carefully, it should have 3 inputs there. So this is the first input, second input, third input. So full adder, I am saying full adder has 3 inputs and 2 outputs. So see here, this is the first input, second input, third input. First input, second input, third input, and 2 outputs. So this is the sum input, and this is the carry output. So 3 inputs, first input, second input, third input, and 2 outputs, sum out and carry out. So 3 inputs, first, second, third, which I am showing with my mouse cursor. See carefully, first input, second input, third input, and 2 outputs, sum output as well as carry output here. So in the initial level, the carry is directly connected to the inputs 0. So 0 is there now. See carefully here. So initially the carry, this is the carry input, this is a carry input, and this is a carry input. Initially I am going to give 0 input to the carry, and that carry is forwarded or propagated to the next level of full adders, and the next level of full adder, and the next level of full adder. In this way we are going to multiply 2 bits, 14 and 10. So 4 bits are going to be multiplied in this way with the help of this Bit Array Multiplier. Is it clear to you? So there are some drawbacks in this Bit Array Multiplier, and the drawbacks are glitching problem is one, potential susceptibility and glitching problem. So this is the first drawback in our Bit Array Multiplier, and second one is delay depends upon full adder. So due to full adder, so there will be some carry propagation delays. So due to that, the speed of the process is also going to be very less. So that's the reason we will go to the next circuit or next array multiplier circuit, which is a Keggstone adder, which will reduce or which will act as a remedy for the drawbacks in Brown array multiplier. And this Cogistone adder is shown here. So this is a resultant circuit of a Cogistone adder circuit. So see here, which follows a carry look ahead adder property here. So we studied that in our previous videos also. Since the ripple adder or parallel adder, ripple carry adder or parallel adder is having a carry propagation delay, so that is reduced with the help of carry look ahead adder. So same way here I used some full adders there parallelly, so it is going to generate a carry propagation. So that is the major drawback. So to reduce the carry propagation in these full adders, so I am going to replace this full adders with carry look ahead adders, and that circuit is considered as Cogistone adder. So this is our Cogistone adder circuit. Okay, and in the next class we will discuss about a clock timing circuits. So this Cogistone adder is a computed fast for computing them in parallel. All action is going to be takes place parallelly in the Cogistone adder. No need to worry, this is not in our syllabus. So the array multiplier is there in our syllabus. Brown array multiplier is there in our syllabus. No need to worry. So there are some drawbacks in this Brown array multiplier. So that's the reason to reduce the errors which are there in Brown array multiplier will be rectified with the help of this Cogistone adder. So that's why I am displaying here a Cogistone adder. In this in this Cogistone adder, all the operations are done in parallelly. So in the next class we will discuss about the clocking of CMOS circuits, our next unit. For any reference, go through the textbook Basic VLSI Design by Douglas A. Pucknell and Kamran Ishragian. Thank you.